Hi. In this video, I'm going to talk about chapter 22 electrostatic and focus on the Coulomb's law. In the previous video, I mentioned that electric force arises from electric charges. And electric charges can be two polarities, either positive or negative. And the electric force can be either attractive or repulsive, depends on the charge combination. Like charges repulse, unlike charges attract. So that's the direction. Force is a vector, so that's the direction of a charge force. But then I haven't mentioned about magnitude of the force. And here, to find the magnitude of the force, you can apply Coulomb's law. So let's see the slide. Let me see here. Okay, so electrostatic force, this is the slide that you saw in previous video. Electrostatic force is a non-contact force. So it's just like a gravitational force. You don't have to be in contact and you have forces. And unlike gravitational force, gravitational force is always attractive force towards each other, right? Earth and apple falls towards the earth, right? But electrostatic force, it can be either positive, attractive, or repulsive. Depends on charge combination. So here, there's an illustration. Oppositely charged particles, object is attractive, but then if you have like charges, either minus, minus, or plus, plus, the force is repulsive. So when you see the two particles that's been separated apart, that means that those two objects have the same charges. Okay. Then those are the directional forces. How to find the magnitude of the electrostatic force? Electrostatic force can be described by the Coulomb's law. So in this, this is Sir Coulomb. In this orange equation here, Fe, the force of electrostatic force, that's equals to, there's some kind of a letter K, and this K is electrostatic constant times Q1, Q2, the charges of two objects, divided by the R squared, the distance of the charges between. This formula of an electrostatic force, the Coulomb's law, look very, very similar to the gravitational force that we just learned. The universal law of gravitation says that G, the universal constant, and times product of two masses divided by the R squared. So they're very, very similar. Okay, I am going to show you. So they're very similar. Chapter 22. Here we are talking about Coulomb's law. So Coulomb's law, I'm just going to give you the, find the magnitude. Oh, sorry. Oh, go up, stay there. Okay. Coulomb's law. Electric force. Static. It's in Newton, right? It's a force, and then it's a vector. So the direction of a forces, if you have like charges, repel, unlike charges, attractive. Sorry. So plus m plus you have, then the direction of a force becomes, this is going to be the direction of the force, minus m minus. But we don't know the length of these two vectors, right? But if you have a plus and minus, then the force becomes this way. So the direction of the arrows changes depends on the charge combination, but the magnitude of the force, this is the direction, and magnitude of the force can be found by the Coulomb's law. What does the Coulomb's law say? The magnitude of the force, which is this one, the Fe, right? Fe. These are the Coulomb force that's applied on each charged particle. And we follow the Newton's laws, equal and opposite, right? And that equals to, there's some kind of a constant. This is called Coulomb constant, Ke Q1, Q2 divided by R squared. So this Ke is called Coulomb's constant or electrostatic constant. Coulomb constant, which is better? Coulomb's constant, electrostatic. So Coulomb's or electrostatic. So this is the constant value. And how much it is equals to 9.0 times 10 to the 9. 9.0 times 10 to the 9 Newton meter square Coulomb square, because the charges Q1 and Q2 are the electric charge, right? So they're in coulombs. It could be either positive or negative, but the direction is just, you know, you're going to see if it's repulsive or attractive, but the magnitude of the electric charges comes in here, Q1 and Q2. And then R is the distance between the two charges, Q1 and Q2. So, let's see. This looks very similar to the gravitational force when you have a G, M1, M2 divided by R squared. Remember, G was universal gravitational constant, 6.7 times 10 to the minus 11 Newton meter square kilogram square, right? It's very similar. And then M1, M2 is the masses, and then R's is the distance. So when we had Earth and Apple, it's an attractive force, attractive. Towards each other. The distance R, the center to the object, right? Something like that. But in the case of this one, you have two particles, like let's say positive and then a negative. Then a distance between R, that's this. And then this could be minus Q1, Q2. Then the forces on this, it's going to be minus and plus, so it's going to be attractive. FE, FE. And then again, FE is equals to KE Q1, Q2 divided by R squared. This is the magnitude. If you have plus and plus Q1, Q2, then forces, then this is the distance between is the R, right? Then the forces applied on these is going to be this direction, repulsive. Again, you can find the value with the KE, Q1, and Q2 divided by R squared. So interestingly, very interesting, Coulomb's law, it's just totally different from gravitational force. It only arises due to two charged particles, but they're both Coulomb's law and gravitational law, they're both non-contact force, and they have the same form. They look very similar. The constant, universal constant times the product of two polarities, two sources for the gravitational force is the mass, electrostatic force is the charges, and they both follow the inverse square law, right? Here, they both follow the inverse square law. Remember the gravitational force, if you go twice the distance, then it decreases by 1/4. 3 times the distance, the intensity of a force decreases by 1/9. Same thing happens with the electrostatic force. Take a look. It follows 1/r squared. So if the two charges separated twice as much, the force of the electrostatic force decreases by 1/4. 3 times apart, it's going to be 1/9 of the force intensity. So it follows the inverse square law just like the gravitational force. Here, you see it. And then you have a plus and minus, attractive, plus and plus, repulsive, repulsive. And then when you draw the distance relationship with the distance and electric force, they decreases just like the gravitational force, 1/r squared. Very similar. So let's see. I mentioned that it is the electric force that's binding, making an atomic shape, right? It's the electric force that's making atomic shape. We say that, let's see, we say that if you have two masses, you always have an attractive force towards each other. Two masses, any two masses always have attractive force. So electrons and proton in hydrogen have one electron and one hydrogen typically. One electron and one proton in hydrogen typically. And so they have both electron and proton, they both have mass. So, and that means that they have an attractive force due to the gravitational force. And the proton and electron also have attractive force because due to the electrostatic force, because it's positive and minus. But I say it's due to the electrostatic force, not, I didn't mention about the gravitational force that's binding the electrons to the proton, right? So is that really true? Let's compare the electric force versus the gravitational force for hydrogen atom. And here in this slide, it says that distance between the proton and electrons, hydrogen is about 5.3 times 10 to the minus 11 We actually don't need to know the distances, and I'll show you. So this one, you don't have to be able to do it. I just want you to just see how we can compare it. So I'm going to show you on the whiteboard again here. Fun. So hydrogen model. Hydrogen have a typical hydrogen have a 1 proton and then 1 electron. So you have a distance between the two particles is r, let's say, and because they have both the mass, one bigger than the other, but you have a force due to gravitational force, Fg. And then because one is positive and the other is negatively charged, so we also have a forces due to the electrostatic force. Let's compare this, which is bigger. So green, let's compare Fg with Fe. Maybe I'm gonna put Fe on top. Let's compare the electric force to the gravitational force on the atom. So apply Coulomb's law. Coulomb's law says Ke Q1 Q2 divided by R squared. And gravitational force says G M1 M2 divided by the R squared. Okay. What's Ke? Ke is 9.0 times 10 to the 9 Newton. Coulomb meter square divided by Coulomb square. The charges Q1 and Q2, they have oppositely charged, but they have the same amount, which is 1.6 times 10 to the minus 19 Coulomb. G, gravitational constant, is 6.7 times 10 to the minus 11 Newton meter square kilogram square. And mass of proton is equals to 1.7 times 10 to the minus 27 kilogram. And the mass of electrons is equals to 0.9 times 10 to the minus 30 kilogram. I want you to notice, pay attention to this constant. So the Coulomb's constant, I don't know if you can see it. The Coulomb's constant is, this is the Coulomb's constant. 9, it's 10 to the 9. It's almost 10 to the 10. But look at this constant. This is 10 to the minus 11. 10 to the 10 compared to the 10 to the minus 11. Right? So let's see. So we're going to put these numbers in here. Equals to, so the Ke is, okay, 9.0 times 10 to the 9 Newton meter square Coulomb square times Q1 and Q2. So 1.6 times 10 to the minus 19 Coulomb times 1.6 times 10 to the minus 19 Coulomb. That divided by R square, right? Divided by the G, which is 6.7 times 10 to the minus 11 Newton meter square kilogram square. And 1.7 times 10 to the minus 27 kilogram times 0.9 times 10 to the minus 30 kilogram divided by r squared. They both have follow the same inverse square law. So this distance between proton and electrons, they both use that for electrostatic force and then gravitational force. So we can actually cancel these because they're in both top and bottom. We don't need to worry about it. So all we need to do is to directly compare these values, right? 9.0 times 10 to the 9 Newton meter square Coulomb square times 1.6 times 10 to the minus 19 Coulomb, 1.6 times 10 to the minus 19 Coulomb compared to 6.7 times 10 to the minus 11 Newton meter square kilogram square times 1.7 times 10 to the minus 27 kilogram 10 to the minus 30 kilogram. You could punch in a calculator to do this, but for physics and science, we often use the order of an estimate, right? So we could actually calculate all these values and compare, or we can actually say this is equals to, let's see. Forget about all these numbers before the 10th. So we have on the top here, let's just compare this and this. I don't know if you can see it. So we have 9.0 times 10 to the 9. So 10 to the 9. And then in the denominator, we have a negative 11. So that becomes positive 11. Sorry. Right? So that's that. And then, let's see. Use the purple, I guess. Now compare this. 10 to the minus 19. So color I can change, I think. It's a purple. 10 to the minus 19. Okay, 10 to the minus 19. And then in a denominator, we have a negative 27, so it becomes 27 plus 27. And then let's compare. Now I can do blue. These. Right? And blue. That's minus, again, minus 19 from the top here, right? Plus 30. So this is called order. We can estimate the order. If you want, this could be like a 10 and then times 10. So this is the same thing as a 10 to the 9 plus 11 times 10 to the minus 19 plus 27 times 10 to the minus 19 plus 30. And you can just add all of these up. And then it's so much easier. It's just addition now, right? Becomes order of a 10. No, 9 plus 11 is 20. 20 minus 19 is 1. plus 27 is 28. 28 minus 19 is 9, and then plus 30. So this becomes 10 to the 39. So Fe is about 10 to the 39 times the force of gravity. It's almost 10 to the 40 because it's 9.0 times 10 to the 9. But anyhow, so that's how big it is. You see that electric force of attractive force is 10 to the 39 times more than a gravitational force. So you can see that electric force is so strong, and you don't need to have a big Coulomb to feel the similar effect of the force. All right? That's why when I say 1 Coulomb is just so much electrons, it's so much force if you have a 1 Coulomb compared to the gravitational force. You see how the electrostatic force. All right, so this is the introduction of a Coulomb's law. Coulomb's law follows very similar to they have the same form as the universal gravitational force. They're both field forces, non-contact force. But you see how strong the Coulomb force can be because of the constant. The Coulomb constant is 10 to the 9, but the gravitational universal constant is 10 to the minus 11. That's to start with. And yeah, you don't need to have a big coulombs to have the similar force effect as the gravitational force. And then again, the difference between a gravitational force and a Coulomb's force is that Coulomb force can be attractive or repulsive. Gravitational force is always attractive. That's all. All right, so this is the end of the video for the introduce the Coulomb's law. And then I guess I'll see you at the discussion.